Hello everyone, and welcome back to another GIS statistics lecture video. And in this video, I want to go through normality in R, how we can sort of go through those 4 steps. Some of this is going to be a review from some of the previous things we've done, and some of it is going to be a little bit more novel to you. So the first thing I want to do is I want to load the iris dataset. And then what I want to do is I want to pull out the Setosa. So we're going to index iris $ species equals, and then I'm going to put in quotes. Actually, let me open up the data set really quick so that I don't make a mistake in spelling this. It's Setosa all lowercase, because otherwise, knowing me, I will make a mistake in the spelling, and this won't work. Okay. Oops. I actually made a mistake. I want to index iris, index where I want all rows where the species equals Setosa. Let's run that instead, and undefined number of columns selected, because I want the rows and I want the columns. There we go. Okay, so now we have Setosa, which is 50 observations. Actually, you know what? Let's go ahead and do this a little bit more simple. Let's do 1, because I want the let's do this a little differently. Let's do sepal length indexed where iris $ species equals Setosa. Oops. Okay. So now we have a vector of values which are the sepal length for Setosa. Now I want to, so this is going to be a sort of realistic variable, and I want to create 2 more. I want to create a normal variable, which we're going to equal R norm. This is a randomized normal distribution, so this is going to be sort of our comparison. This is coming from a normal distribution, so we would assume that this is going to be very strongly normally distributed. And then I want to do a non-norm. And this is going to be from a uniform distribution, and we're going to pull 50 observations from that. Okay, so now over here we have Setosa, which is a realistic variable. We have 50 observations directly from a normal distribution, and then we have 50 observations taken directly from a uniform distribution. So first things first, let's do the mean of Setosa versus the median of Setosa. You'll see here that these are actually very close in value. So this is a strong indication that the Setosa data set, or the sample, is most likely normally distributed. Let's go ahead and let's do let's do norm, right? Mean of norm versus the median of norm. So here, right, we see that in this case, our mean and our median are actually quite different. So in this case, right, we may have an issue, and it would be due to our sample size. Actually, here, let's create one more variable just to sort of prove that I'm not crazy here. Let's do a large norm. And this is going to deal with the issue of only having 50 observations. Let's do 10,000. Okay. And let's do the same thing here. Let's do the mean of large norm versus the median of large. Help if I spelled median correctly. It would help if I spelled norm correctly. This is why you don't do live programming, right? And so just to sort of verify that we're starting to end up somewhere good, the idea of this sort of the normal distribution that our norm is pulling from has a mean of 0. That's sort of the goal. So the fact that both the mean and the median are really close to 0 is a good indication that we're actually where we want to be. All right, so this large norm is going to be far better than the regular norm, simply because we only have 50 observations. And finally, let's compare the mean of non-norm to the mean of, compared to the median of non-norm. So this is where things get a little bit tricky. And we're going to look at the histogram, and you'll kind of see why the non-norm in this case is going to look like a normal distribution, even though we know that it's not. So that's comparing the mean to the median. The next step is histograms. So we can use the hist function in base R to look at setosa. We can run that again. So we can use the plot here. Right, and you'll see that we see that it's mostly bell-shaped, right? There's got a nice sort of bell-shaped curve to it. And again, the critical issue here, we're really lacking from a small sample size, right? We only have 50 observations. So this makes things a little harder. Our sample size here is pretty small. So this is probably not the best example, but again, right, just to sort of go through the steps. So let's look at the hist of norm. Right. So you can see here that we've sort of shifted slightly away from the center. Right? Remember what I said? You want the middle of your bell curve to be sort of in the center of your graph, and you can see here that we're not perfectly there. But again, you can see the bell curve, and as I mentioned before, we're really suffering here from a small sample size. And to sort of prove that, let's look at large norm. All right, you can see large norm, now we have a much better bell shape, and it's much more centered in terms of its values. So this is what you would really want to see. And again, this is with 10,000 observations versus 50. So you can really see the effect that small sample size was having. Finally, let's look at the non-norm. And this will explain why we have that weird issue with the mean and the median being so close together. So if you look at the histogram, right, this is clearly not a uniform distribution, but the reason that the mean and the median were so close together is because the mean is going to be, right about here based on the number based on the average. But again, because pretty much all values have the same frequency, or there's a little bit of a discrepancy here, but again, a small sample size, right? You're going to end up with the median also being, somewhere in here. So that's why I said you always want to go through all 4 of these, right? You want to check your mean versus median, you want to check your histogram, your QQ plot, and then run that statistic. Because a uniform distribution, which is the distribution we use to get this, right? The mean and the median are going to be similar just because of sort of the distribution that we pulled from. So let's do a so that's our histograms. So let's do our QQ plots. So the first QQ plot, in order to do a QQ plot, you're going to do QQ norm. So this is going to create a QQ plot from a normal distribution. You're going to pass in your data. So in this case, we're going to pass in Setosa. All right, and you'll see that what we've done is we've got the theoretical quantiles, right? These are what you would expect, and these are what we actually got. And you'll see that what we've done in this case is we've plotted the lines, or plotted the points. If we want the line, you have to do QQ line of Setosa and run that. Okay. So to recap, right, the whole goal here was that we have this expected relationship, which is the solid line, and we want most of the dots to be fairly close. And you'll see here that this is actually what we observe, right? There's a little bit of deviation up here, but by and large, they're pretty close to the line. So I would say this is a good indication that the data is probably pretty close to normally distributed. Again, we have a small sample size, but what are we going to do? Right. So let's look at the QQ norm of the non-normal. Right, QQ norm, QQ line of non-norm. Right, so here, right, even with 50 observations, you're really now seeing that difference, right? Because the non-normal, you have a lot of values up here that are deviating quite far away from the line. You have a lot of values in the lower end that are deviating quite far away from the line. So this is a good, strong indication that that non-normal, right, that uniform distribution, right, is not a normal distribution. Finally, just to sort of prove things work, let's do QQ norm of our large norm. And then QQ line of large norm. Right, again, we see we have a very strong, tight connection between the points and the line, indicating this is basically coming from an almost perfect normal distribution, which we would expect given that we sampled it from the definition of a normal distribution. So finally, that's the QQ plot. Let's do the Shapiro-Wilks test. Shapiro-Wilks test you get by typing in SHAP. You'll see that it auto pops up Shapiro.test. And again, the contextual menu says performs the Shapiro-Wilks test of normality. So if we hit enter, it will auto complete that for us. And we're going to run it on the only variable that it intakes, or the only parameter that it takes, is x, which is the data that we want. And in this case, we're going to pass in Setosa, and we're going to run that. And you'll see that what we get is the Shapiro-Wilks test for normality, data, again, Setosa, and then under here, we get the W, so this is the test statistic, and then we get this p-value. So again, Shapiro-Wilks, right, the null hypothesis is that the data is coming from a normal distribution. So in this case, the p-value is greater than 0.05, so we would say that we are comfortably not rejecting the null hypothesis, right? So we are comfortable stating that that we got this data or this sample given that the population is normally distributed. Okay, so hopefully that makes sense. So let's just go ahead and run another one. Let's run one on the non-normal. On non-norm. Okay. All right. So in this case, right, our W, we have the test statistic. And in this case, our p-value is much less than 0.05, right? Our traditional alpha. So in this case, we would say that we feel comfortable rejecting the null hypothesis. And so what that means is we do not feel comfortable saying that we got this data given the population is normally distributed, right? So we're sort of rebuking that. We're saying that it is most likely that we reject the null hypothesis, right? So this data is most likely coming from a population that is not normally distributed. So again, p-value greater than 0.05 most likely is normally distributed. P-value less than 0.05, right? We're failing, or we're rejecting the null hypothesis. So we're rejecting the idea that the population is normally distributed, or that we got the sample from a population that is normally distributed. Hopefully that makes sense. Again, a couple of these lines of code were probably new to you. If any of this was confusing, I encourage you to go back, rewatch the part you're confused about. And as always, please reach out. Thank you.